Okay, folks, we're back. So just continuing on here, this will be volume 2 of Equilibrium Mathematics. So if you want to kind of index it with what the YouTube videos are, we'll continue on there. Actually, I think I made a mistake. You should be able to finish problem set number 1 with no problem now. I kind of gave, I said in the last one you should probably be able to do problem set number 2, 1 through 3. I doubt you could do those until this video, unless you read ahead and did them on your own, which is fine. We're still in section 13.2, and I'm still indexing everything here to the slides. The examples I'm going to write up here as we go along. So I'm looking at my slides right now, and we did homo and heterogeneous equilibria last time, and I actually forgot an example for homo and heterogeneous equilibria, so this is just another one. It's just to kind of click back if you want to. So you have solid carbon reacting with gaseous sulfur and producing gaseous sulfur dioxide, or I'm sorry, carbon disulfide. So if you want to, just take a second to do the Kc and Kp expressions for this, noting that it is a heterogeneous equilibrium. So if you want to stop the video, see if you can do it, and then I'll write the answer. Okay, so that should be pretty easy. I just forgot that one in my notes, just as a separate example. Okay, so we're going to finish off this chunk, and the next video will actually be homework help on Le Chatelier's principle. I'm just going to do a couple of problems from the homework there to help you along, but it'll be a really short one. You may not even need it. Okay, so we're in the notes, and I'm just going to show you a derivation. I'm not going to expect you to be able to derive this, so what we want is a way of converting between these two measurements of equilibrium. And I believe that this ultimate mathematical formula that I'm going to derive, and I'll put the answer down here, is on your equation sheet that I gave you earlier that you'll be able to use for every quiz and test from here on out. So you don't have to memorize this derivation. I just want to show you where it comes from. It's kind of interesting. So this involves pressure, this involves concentration. We actually use an equation that you know quite well to relate concentration and pressure. Okay, so you know PV equals nRT is the ideal gas law, that's fine. I'm just going to do this manipulation, dividing side by the volume and combine it with the moles. I think we did something like this before. This is moles divided by volume. And in the ideal gas law, it's moles per liter. Well, that's the same thing as molarity. That's what that is. It's molarity. So, okay, so that means that the pressure is the molarity of the gas times RT. That's probably not too bad of a manipulation. And then what we can do is we can use this relationship to relate a Kp and a Kc. I'm just going to do this for a generic reaction. This is the same way every book does it. Your book shows you this very explicitly in section 13.2 if mine doesn't make sense. So let's just take this generic reaction. I'm just going to blast through this. And and let's assume that these are all gases. So it's homogeneous. We're not having that complication. We've done that lots of times. We did this for Q and K. So, since these are gases, let's just do this. So it's going to be that's pretty generic. Products over reactants. Make sure you always do that. And then we can actually then make a substitution here. Molarity RT for each of these. And R and T, by the way, are going to be constants. We're going to assume that this equilibrium takes place under a constant temperature, and R is the ideal gas constant. So these two we don't even have to bother with all that much. It's the molarity that we could substitute here. So I'm going to kind of jump ahead. And let's see, how can I do this? Actually, I'm not going to do that. Let me just make the substitution now. That whole thing raised to the C power. Okay. And concentration of D, whoops. Concentration of D, RT, raised to the D power. Yikes, it's looking complicated. Okay. Times the concentration of A, RT, that whole thing, to the A power, and then okay, I think I did all that right. So here's what I'm going to do. I'm going to pull out the RT. Now, this may not be something that you're familiar with from mathematics. So, when you have exponents like this, C and D, you can add those together. And down here, you can add those together. And when it's numerator, denominator, you can subtract them. I'm not going to bother with the algebra too much here. I think it'll make sense when you kind of look in the book. So what you end up doing is, I'm going to pull out the concentration terms. That's a legitimate move. I can just pull those out, right, rewrite them, and then okay, so I just took all the concentration terms of those powers and pulled them out of everything else. Now this actually, that's Ka, or excuse me, K. That's Kc. That's an equilibrium constant based on the concentrations. If I asked you to write Kc for this one, that's what you would write. So that is Kc, but what about all that RT business? Well, okay, now you have to take my word for this one. I think you can probably figure this out. What is left here? Okay, if I'm going to combine all of these RTs into one term, it's going to be C plus D minus A plus B. Now what are C's and D's and A's and B's and all? Those are just the coefficients. That's all they are. They're the coefficients in front of these problems. We're going to do one of these here in a minute. So you take the coefficient in front of C, add to that the coefficient in front of D, now that looks super complicated. That looks like a really complicated equation, but there's actually a better way that we have to write this one. Here's the equation you want. Let's see, Kp equals Kc, that's all that is, RT we replace this complicated looking thing with this very simple thing. It's the change in moles. So I have C plus D moles as your final state minus A plus B moles as your initial state, a delta like we always do. So it's a change in moles. So if that's a 3 and a 4, it would be 7. And that's a 1 and a 1, that would be 2. So it would be 7 minus 2. We would put a 5 there. That's all that means. So this is an equation. We're not going to use it a ton, but it's a useful one occasionally. And it's an easy one, I think, after you see the derivation. So let's actually do an example. I think I've got one here. Yeah. So I need some space. And I'm going to go back and use an example we did before. What did I give you before? Yeah, okay. I think we did this one already. So example one, I think I gave you a KP, and now I'm asking you to find the KC. So this is the same reaction we seem to always do. Putting that there for emphasis. Let's just do the delta N part first, because I think that'll be easier. So delta N is going to be 2. That's the only thing over there. That's not like there's another one over here. Minus 3 plus 1. So final moles minus the initial mole. So wow, we get a negative 2 number. That's weird. Okay. But that's what it is. So we're going to have to put, when we put the numbers into this formula, we're going to have to do this. Now, let me take my word for a couple of things here. Let's see. So we want to put in KP. All right, well, well, we're trying to find KC, aren't we? Okay, well, that's what we're trying to solve for. And we're putting in RT. Now we're using the old form of RT from the ideal gas law. So this is 0.08201 liters atmospheres over Kelvin times moles times temperature. I don't have the temperature written down in Celsius that I gave you before, but you can go back and look. I'm pretty sure that the temperature in Kelvin is going to be 573 Kelvin. So R times T, all of that raised to the negative 2 power. That's kind of odd. It's like a reciprocal squared is really what it is. Okay, now, we have to check out the units here. It's liters, atmospheres, and Kelvin moles. You might recall that I gave you a KP in milliliters of mercury before. We can actually just convert that into atmospheres, because 1 atmosphere is 760 millimeters of mercury, so the ratio turns out to be the same. So we still could use this number now before, we put here mmHg to the negative 2. But you can convince yourselves, if you did the conversion, the atmospheres would be just fine. That conversion factor of 1 atmosphere is 760 millimeters of mercury. That would all just cancel out, and the number would actually end up being the same. So this is a legit move. Now, so what does that mean? That means that Kc is this divided by all of that. Oof, it's going to be kind of big. So we're going to have 4.34 times 10 to the minus third atmospheres to the negative 2, bizarre units to follow, divided by 0.08201 liters atmospheres over Kelvin times moles times 573 Kelvin. So right away we can cancel that. These are going to be some strange units. And to be honest with you, we're not really concerned about the units of equilibrium constants all that much, because they get so bizarre. And I'm going to let you sort through this one here a little bit. Because if you do this math, let's see, you're going to get, well, I'll just give you this part. If you do all of this math here, just multiplying those two, you're going to get, let's see, 47 0.0 liters times atmospheres over moles. Okay, but then you have to take that to the -2 power and do all of this math, and you should end up with a Kc. Now you can work through this, or let me know if you need more help, of 9.61. And if you do the units, you're going to get liters squared over moles squared. Oof. Again, I'm not that worried about it. But that's actually the inverse of molarity. So you're going to get 9.61 molarity to the second power, which kind of has to make sense. Because the Kp has units of atmospheres to the -2. Kc should be concentration units to the -2. So that those exponents should match up. So see if you can do that math and regenerate this answer. Okay, so that's going from a Kp to a Kc. And if you want to stop the video and kind of work through that one on your own, there are a couple of homework problems where you do that. At least the first homework problem, determine the values of Kc from the given Kp with appropriate units. And there's 3 of those, and you're given the answer. So if you want to go do problem set number 2, number 1, that would be fine. Okay. The next ones don't involve a ton of math, so I'm not going to do, well, they involve some, so just give me a second here to erase. So that's calculating a Kp from a Kc. And the last thing, if you want to look at your notes, we'll do number 4. Oh, I'm sorry, I really wasn't doing the notes very well. I think I did number 3, Kc and Kp. Yeah, okay, these I don't think are too bad. I don't know if you remember from thermodynamics, like when we took an equation, like say it was exothermic with a negative value and you flipped it around for Hess's law, you had to make the value positive. And vice versa. If it's endothermic and you reverse the equation, you make it negative. Well, this is kind of the equilibrium version of that. I'm going to tell you what the answer is before I even show you. So when you write an equilibrium, you have the forward reaction and the reverse reaction. The equilibrium constants are the reciprocals of each other. It's not negative, because that's not the math. It's not products minus reactants, it's products divided by reactants. So it's just, you just flip the equation around. But it's not that tough of a concept. Okay, so gee whiz, I'm getting a lot of mileage on this one. I'm going to stop writing the subscripts. So K forward equals, I'm using concentrations, not pressures. It would apply to both concentration and pressure, by the way. If we did the reverse reaction, I just took this thing and flipped it around. Well, okay, it would just be the reciprocal of this. Okay. It's just a mathematical move that comes in handy from time to time. Is that right? Yeah, it's just a reciprocal. They're reciprocals. Not too bad. think I can fit this one in here. Another thing you might remember from Hess's law is that if you have an enthalpy and you have to change the coefficients, like divide them by 2 or multiply them by 3 to get the equations to add together, if you don't remember that, don't worry about it. That's the version that we're doing here, is what if you have to manipulate the equation a little bit? That's why this whole section is called manipulations of K. So what are we doing here? This is B. So changing the coefficients in the chemical reaction. We won't normally have to do that, but it's just something we show you. Okay? Yeah, okay, I'm just sticking to the same equations here. All right, I'm just going to show you 2 examples side by side. What if I take all these coefficients and double them? Which is not really something we would normally do. So we put 2 there and a 4 there. And in the second example, I'm reaching back for a definition. A thermochemical equation is where we always produce 1 mole of our primary product. So I would have to divide through all these by half. So I'm dividing by 2 here and I'm multiplying by 2 there, just to make it the same point. So this is going to be 3 halves H2 plus 1 half N2 in equilibrium with ammonia. Okay, so strictly speaking, if you're going to write, let's see here, Kc, and I'm going to call this, since a manipulated equation, oftentimes what you do in science, when it's a slight variation of the original Kc, with the original, you put a prime. And over here, I'll call this Kc double prime, because it's a small variation of the original normal balanced chemical equation. So in this case, it would be, well, ammonia over hydrogen to the 3 halves power, which is kind of a pain, times nitrogen to the 1 half power. Strictly speaking, well, that's the original equilibrium constant that we've been using all along, raised to the 1 half power. So if I take 2 times 1 half, that'll be 1. If I take 3 times 1 half, that'll be 3 halves. So all we do in this case, oh, by the way, 1 half power is the same thing as square root. Okay, so we can actually put in a number here. So we could take the 9.61 that we calculated before, inverse molarity squared to the 1 half power, and just crank that out and get a number. Well, I'm going to do that. You can do that. The square root of 9.61 is going to be 3 point something or other, and you can fill that out, and then the units will just be inverse molarity to the first. So that's fine. You basically take the original equilibrium constant and take the square root. Now over here, well, I think I can convince you of this. We double the coefficients. I'm not going to write all that out. So in this case, this new equilibrium constant would be the original one taken to the squared power. So we would have to take 9.61 and then square it. Now that's just something, we're not going to dwell on that one. There's just some easy, well, fairly easy problems to do in the book on that. That may be getting down close to where I want to finish. with this one. Oh yes, and multi-step processes. Sorry about that, I kind of forgot that one. So double check here and see if you need anything else, and I've got to fumble around in my notes just briefly. Ah, here we go. That's A, B, then we have C. Just don't have any room. The last one is if you have two equations, chemical equations that you add together, like we also did with Hess's law, before you add the enthalpies. In this case, if you add two chemical equations, you multiply the equilibrium constants to get the overall one. So it's basically taking addition and changing it into multiplication. So this is C. We don't do a lot of this in chemistry class. We assume we have one chemical reaction that goes from A to B or whatever. A plus B goes to C plus B, and it's done, one process. But oftentimes you have multiple steps that we've talked about before, but in this case it's pretty straightforward. Let me just show you one. Okay, you might just want to give me a second here. So say the overall reaction is this, and this is a reaction that would take place in the atmosphere. This is a reaction that generates smog. So this is in equilibrium with NO2. By the way, these are all gases, so I'm not going to take time here going G all over everything. So go ahead and do that. So in this case, it's nitrogen plus 2 oxygens in the atmosphere producing 2 NO2s. Now this is a brown gas. This is one of the things that contributes to smog, that brown haze that you sometimes see. And when this mixes with water, you get nitric acid. That's called acid rain. So this is the overall reaction, and we could write an equilibrium constant expression for that, and that's fine. It would just be this squared divided by this times this squared. Fine. Products over reactants. But in this case, it's a two-step process. Step 1 and step 2 that add to give this overall thing. So the first thing that happens in this chemical reaction is the nitrogen combines with one of the oxygens. It's kind of like a reaction mechanism from kinetics, which is exactly what it is. This is a reaction mechanism. And you get 2 NOs, nitrogen monoxide, which doesn't even appear in this equation. Well, that's because the second step are those 2 nitrogen monoxides reacting with the other oxygen to produce 2 NO2. So this is a 2-step process leading to this overall thing, and this is an intermediate, kind of like an intermediate in a reaction mechanism from kinetics. And I'm actually not going to write out the math. You can do this one for you. So we would have so K overall. Maybe you can convince yourselves of this. When you add steps, you multiply the equilibrium constant. So if you want to know, and you'd have to give it values for this, I'm just showing you the derivation. The K for this overall is going to be the K for step 1 times the K for step 2. Now you can actually show this K and multiply them. Well, what's going to cancel? That's going to cancel. And you're going to be left with this. So it's not that difficult to do. So overall is the case overall. And I think that would be good. That should let you do, yeah, you should be able to do the first 3 problems in problem set 2. I don't give you a ton of problems on these. So at this point, problem set number 2, you should be able to do 1 through 3 completely and not be a big problem. Okay, just a quick thing, I'm not going to come back to this one. Questions 4 through 7 are qualitative. they're Le Chatelier's principle problems. I'm just going to do a quick homework problem help video. I'll do one of those, but that's where you may want to come back and ask me for some additional help before we move on. Okay, so that's it, and hopefully, hopefully this will be true, make these videos a little bit shorter. Take care.